Hi, this is your lesson on inertial and non-inertial frames of references. We've previously discussed inertial frames of references as being frames of references or perspectives that we can observe a motion of an object that are at rest or moving at constant velocity relative to the motion of the object. Here's an example to illustrate what we talked about previously. The skateboard is moving at constant velocity, and the ball is at rest relative to the frame of reference of the skateboard. Of course, if you wanted to observe the motion of the ball from the frame of reference of the ground, we could say that the velocity of the ball is the same as the velocity of the skateboard from a stationary frame of reference. So we know how to do that. We know how to put ourselves into and out of certain frames of references in order to describe the motion of an object. What happens though if that frame of reference is accelerating? A frame of reference that is accelerating we call a non-inertial frame of reference. So a non-inertial frame of reference is a frame of reference that accelerates relative to an inertial frame of reference. That is the ground in this case. We're standing still on the ground. We see the skateboard move past us. It accelerates, so it either speeds up, slows down, or changes direction. And this time the ball doesn't stay put. The ball's velocity relative to the skateboard is no longer zero. If the skateboard is initially at rest and we give it a shove and accelerate it in this direction, the ball relative to the skateboard will move towards the tail. In fact, it will accelerate towards the tail. If we're on the skateboard with the ball, that is, our observation post is at rest relative to the frame of reference of the skateboard, it will appear like some magical force is pulling the ball towards the tail. This is our topic for today, to explain these things. And to do so, we will take a look at a couple of examples. We'll calculate the acceleration of an object in a non-inertial frame of reference, how we can make sense of those, and also draw a free body. Before we take a look at those examples, let's delve a little closer into the definitions of inertial and non-inertial frames of references. We call inertial frames of references inertial because it relates to Newton's first law, that is the law of inertia. And what inertial frames of references means is that the first law of Newton, that is the law of inertia, is true. It holds, it makes sense that an object will continue to stay at rest or at constant velocity until acted upon by an outside unbalanced force. A non-inertial frame of reference, then, is one in which the law of inertia does not hold. The law of inertia does not hold. What that means is, apparently, if we're in the accelerating frame of reference, the object that's moving, the yellow ball moving towards the tail, has no visible force acting on it, but it seems to be accelerating nonetheless. So there is no force acting on that yellow ball, pulling it towards the tail, but it sure looks like there is, from the perspective of the non-inertial frame of reference. Weird things happen in non-inertial frames of references. You can appreciate this when you're in a car and you've got a hot coffee and you're a riding passenger and you're about to take a sip, and the driver decides to accelerate in a rather aggressive manner. What happens? Well, the coffee is splashed into your face. That's strange to us that the coffee should jump out of the cup and into our face. We think there's some force acting on that cup, moving it towards our face. Now, it all kind of makes sense, though, if you look at the whole accelerating frame of reference from a perspective that is stationary, because all you really see is that the yellow ball in this case is just trying to stay at rest. It's trying to stay where it is, and it's the skateboard, the frame of reference, that is accelerating away from it. So from the perspective of the ground, a stationary frame of reference, it kind of makes sense to us that an object is going to want to try to stay at rest, and it needs an outside unbalanced force to accelerate it. So the ball really, from our perspective, isn't moving. What's moving is the skateboard under it. This leads us to make up names for these apparent forces that cause objects to act strangely when we're in a non-inertial frame of reference. And you'll hear a couple of terms that we use in order to describe these apparent forces. One of them is a fictitious force, which we can define as an apparent, but really non-existent force which we invent so that we can explain the motion of objects and here's the important point: within accelerating or non-inertial frames of reference, we call those fictitious forces. We can call them apparent forces. We can even describe them as inertial forces. You may hear that term around as well. Fictitious force, inertial force, and apparent force. The classic physics demonstration of this usually involves a bus, not a VW bus, but a school bus. And there's a passenger seated on the school bus, and on the floor is an orange. Now this bus is currently at rest, and we have an observer on the ground. We have two frames of references. We have this inertial frame of reference of the stationary bus, and we have our frame of reference observing the behavior of the bus and its contents. Both frames of reference are inertial. That means they're at rest relative to each other or traveling at constant velocity relative to each other. Let's say now that and nothing's strange, the orange isn't floating up in the air, it's not rolling any direction, nobody's feeling any funny things in their chest, everything is fine. If this bus is traveling at constant velocity, we also observe that everything is normal, that the law of inertia holds. The orange is at rest relative to its frame of reference. It's moving at constant velocity relative to us. All the laws of physics are true. Everything is fine. As soon as we get that bus accelerating now, let's say that that bus accelerates towards the right aggressively. a couple of things are going to happen from the perspective of us on the ground. The orange is going to attempt to stay where it is while the bus changes its position. And so did our dude here. Let's redraw him. Now this is strange to only the observer who is seated on the bus, because the orange has a motion that has moved it, accelerated it towards the back relative to the observer on the bus. And so he thinks some force must be pulling that orange towards the rear of the bus. But from our perspective, we see that the orange really didn't move at all. And the orange will attempt to stay where it is relative to our frame of reference until the back of the bus smashes into it and we make orange juice. Now let's develop this a little bit further and put some math to it. Let's say we have this bus frame of reference again. And from the ceiling of that bus, we have a rubber stopper. As the bus accelerates forward, you can imagine that this cork is going to change its orientation. It's going to appear to swing backwards. Now we can use this because we can measure the degree of swing, and by the behavior of the apparent force acting on this rubber stopper, we can come up with a value of the acceleration of the frame of reference. Let's take a look at how we can do that. Let's draw a free body diagram of that rubber stopper. So there's a rubber stopper. We have Fg acting downwards towards the ground. But when it is at this position, as the bus is accelerating, we have a tension force in the string that's angled up at some angle. And that angle, let's say, is 10 degrees. Let's see if we can use our forces laws, F net equals ma, and the sum of all the forces, in order to come up with what is the acceleration that is needed to cause this apparent force to be operating. Okay, well, let's label up some stuff here. We got an x component. We can say that this is the x component of the tension force, and this is the y component of the tension force. We can come up with a description of the y component of the tension force. It is whatever the tension force is, this vector here, multiplied by the cos of theta, and the tension force, the x component of the tension force here, is going to be the tension force, which is the hypotenuse, multiplied by the sine of theta. All right, let's see what we can do. Let's take a look at the y forces here. Well, the sum of all the forces in the y direction is going to be 0. This object isn't apparently accelerating up or down. It is accelerating towards the back of the bus. So we can say that the sum of all the y forces must be 0. Let's list all the y forces then. We have mg, and we also have, which is pointed down, so we can call that negative. And then we also have the y component of the tension force. And that's all set to 0. So we can say that Ft cos theta is equal to mg. And so the tension force in the string, and I'll show you why I'm simplifying in terms of the tension force, is going to be mg divided by cos theta. Now you may be asking, well, how is this helping us find the acceleration? Well, we're just playing around with descriptions of the forces that are at work, hoping that we'll arrive at some description of acceleration in terms of the forces that are at work. And you may be able to see why we're doing that. Let's take a look at the x components of the forces. The sum of all the x forces has to equal the mass times acceleration. Well, there we go. Okay, so if we can describe the sum of the forces in the x direction, then we can find the acceleration. Let's forget about mass for now. You may see that mass could possibly cancel out. The sum of all the forces in the x direction, well, there's only one, and that is the x component of the tension force, which is Ft times sine theta is equal to ma. We have a substitution that we can perform here. If we substitute in equation A into Ft, we may be able to simplify further and come up with a description of the acceleration. Let's do that though. So we have mg divided by cos theta multiplied by sine theta is equal to the mass times the acceleration. We have mass here applying in the same manner to both sides, so we can cancel those guys out, negate their effects because their effects are the same on both sides of the equation. And so we're left with little g multiplied by sine theta divided by cos theta, the simple rearrangement there, is equal to the acceleration. And then you may realize that we do know theta. Our theta is 10 degrees. So we have little g multiplied by the sine of 10 degrees divided by the cos of 10 degrees. Some of you may realize, well, the sine of one angle divided by the sine of the same angle is equal to tan of that angle. And that's equal to acceleration. When we plug our numbers in, which I won't show you here, we find that acceleration is equal to 1.7 meters per second squared. So we use the substitution here in order to describe the acceleration in terms of the apparent force as observed from inside the frame of reference, that is accelerating. Not sure what's going on there. So we can see that we can use the strange behavior, these apparent forces, to arrive at descriptions of motion of an object. I'll give you a little bit of work. A lot of these things, these types of questions for inertial and non-inertial frames of references, you really need to do the force diagram in order to explain what's going on. And you also need to state the frame of reference. In this case, the frame of reference was the accelerating bus. You need to be able to put yourself in and out of different frames of references in order to arrive at these conclusions. All right. Well, that's all for inertial and non-inertial frames of references. We'll catch you later.